Hi everyone. Today we are going to start you a filter design, but in terms of the finite impulse response or the FIR filter. Okay? And so, as always we do, we need to add some titles in here. Digital signal processing. Okay? The first topic is about our lecture is that the finite impulse response filter. Okay, as in the name, this is a finite impulse response. What's the meaning of the impulse? At each case we need to take the impulse values from this filter, and then we need to design a finite or the limited some regions for the for the discrete domain. Okay, and so what's the difference between the IRR, infinite impulse response filter? We must first say that we have up to now we have dealt with the IRR filter, because just like in the low pass digital filter, which is designed in the previous lecture, this is called the IRR filters because it has a feedback. Okay. And so before begin free filter, we need to describe the differences between of them. Okay, so first title is that the IIR filter. Okay, in the IRR filter its output, it's determined by both to its current and past inputs and past output values. Okay, we can write this equation in here just like this one. The yn is the filtered response in here. And so we can collect all the terms at the firstly beginning with the k is equals to the 0 and m, and a k times y n minus can. This is a backward index in here just like this one. And also we should collect to the the k is equals to 0 up to the n, and be k times x n minus k. Okay. This is the the feed forward coefficients. This is the feedback coefficients. Okay, because it's a filtered response, this is the input. Okay. And so also this AK and BK is considered as the filter coefficients. Okay, so in the Z domain we have this pulse transfer function as to the hz is equals to the k is equals to the 0 up to n, and bk times z over minus k, 1 minus k is equals to the 0 up to m, and a k times z over minus k. Okay, and so in order to design the R filter, low pass or high pass in here, we need to check only the poles, okay, in rock region of current state. Okay, and so it has a feedback in here. Okay, it has a feedback. What's the feedback? Feedback means that y and minus k. Okay, and so which means that it always generate a response like this one. For example, in the Bode plot we have the what, this frequency values in here, and we can draw the cutoff frequency in here just like this one, and so we can design the R filter in the dB 0 dB, which is that what the maximum flat values at the what at the cutoff frequency, and after the cutoff frequency this closing to what to 0. Okay, but it always or it cannot be 0. Just remember the discrete low pass filter design. If we apply the any signal that's bigger from the what the cutoff frequency, for example the 500 sinusoidal signal, and then we will have or we have obtained to the what to the some output for a given signal. For example, if the input signal with the amplitude of the 1 we have at the 500 hertz, and then we will have 0.1. okay, it always creates the signal. Or if we get the higher frequency, maybe this happen, for example 500 kilohertz, for example 500 hertz inputs. Okay, and so this is the input, this is the output. This is our case for the what, for the IIR filter. Okay, and also we need to know that this filter is designed in the linear domain, otherwise we cannot plot or draw the Bode response of these terms. Okay, and so we don't have any nonlinear filters in here, otherwise we cannot take the Z transform or we cannot apply the Z transform in here, just like this one. Okay, and so in the IRR filters we can draw to what the disadvantages in here we can say about it. Okay, first of all we need to write that we cannot easily build linear fuzz for or causing the timing problem in here. Which means that if we apply the what the 500 hertz signal to this filter, and then maybe we have the minus 45 fuzz degree in here, but always we have this kind of nonlinear curve at what at the fuzz degrees in here. But if we have the linear fuzz in here just like this one, and so we can easily control the output signal in here, because in one cases maybe up to 1 second we may have the 500 hertz at the input signal, but up to 1 to 10 maybe we have the 500 kilohertz signal. Which means that this the transition fuzz may be corrupted due to these regions. Okay, also stability of this filter is not guaranteed. For IIR due to the what? Due to feedback components. Okay, we should always check the values of these terms, okay? And also IIR filters as a result are closed loop system. When the finite impulse response filter is an open loop one. The FIR filter does not require any feedback components in here, but the IR should always take into the storage the past values of the R input signals and the filtered signal itself. Okay. For example, first order FIR filter can be designed with to the yn and xn minus 0.9 times yn minus 1. Okay, this is simple case for the IIR filter, infinite impulse response filter. Okay, in the Z domain we can translate the whole pulse transfer function into the 1 divided by 1 plus 0.9 times z over minus 1. Okay, this is the representation of the first order IIR filter. Okay, this maybe creates the low pass characteristics at these times. Okay, and so the R or in the previous lecture we have designed to the discrete low pass filters, which is called to the infinite impulse response filter. Okay. But we may choose another properties or another filters in here. FIR filter. Okay, and so its output is determined by the sum of the current and the past input samples. Okay, it's coming from the outside, and then we can write it just like this one, yn, which is equals to the k is equals to 0, and so n minus 1 bk, it's the filter coefficients in here, x n minus k. Okay, and so this is the input, this is the coefficients, feed forward coefficients, and then we can design to this filter. But in the Z domain in Z domain h z is equals to the k is equals to the 0, n minus 1 bk times z over minus k. And so in this case we don't need to check zeros, because at each case if the R input is bounded, and then this yields the bounded signal because it's the open loop response of these terms. But in the previous case we have the closed loop response or the feedback, and so this feedback may continue growth or the decrease to the values of the watts with respect to the input signals. But in the FIR filter we don't have any stability issues, just like this one. Okay. And so how can we say about or describe the advantage of this filter? Advantage of FIR filter. First of all, we can say that the FIR filters is the inherently stable. since we don't need to use the feedback. Okay, and also FIR filters can be designed in linear phase, which means that all frequency components of the inputs are delayed by some amount. Okay, so which means that all frequency components of input are delayed by some amount. Okay, which means that we can use the delayed operation or the delayed application on this frequency, because if we have the signals containing to 100 and 500 kilohertz signals, and then we can easily set the same delayed operations at this moment. Okay, especially for the real-time application, this is important, guys. Okay. So for example, we can write the examples of this one. The FIR can be given by to yn, which is equals to the 0.5 xn plus 0.25 xn minus 1 plus 0.25 xn minus 2. Okay, and so we can write this filter in terms of the hz, which is equals to the 0.5 plus 0.25 z over minus 1 and 0.25 z over minus 2. Okay, this is also equals to the yz for a given x, z values. Okay, this is the transfer function, but this transfer function, it's to is open loop response, which means that we don't have any closed loop roots or the poles or the z domain roots, and then we can create the stable response in here with with the linear fast components of these signals. Okay, just like this one. After that, we should write a remark in here, just like this one. In order to create or design these filters, steps to find the cutoff frequency. This is important part. Okay, we have the procedure for this component. Procedure like to the z is equals to the a exponential term over j w. Okay, and so w is also equals to the 2 pi f divided by fs. Fs is the sampling rate, and the condition the condition is that fc or the cutoff frequency is indicating with 2 minus 3 decibel, which is equals to the 20 dot log basis 10 0 7 0 7 at the half of the power. Okay. This is the same as with the with the continuous one. Okay, in this case we have only looking at the magnitude response to catch the half power rate, just like in the in the continuous domains. Okay. So the steps are, or can be summarized like just this one. Obtain the transfer function of R representation as hz in the discrete domain or the z domain of the IIR filter. Okay, for this case this is the IIR, or we can use the FIR filter. Okay, and after that the substitute the z is equals to the E over JW into what, the HZ to get to what, the HE over JW. Okay, and after that we need to calculate to what, calculate absolute values of the what, the E JW. This is the what, the magnitude of the R response or the filters. Okay, and after that we need to solve the R system to the what, absolute values of the these terms, which is equals to what, the 0.07 to get the what, V, right, in terms of to what, FC, which is equals to W Fs divided by 2 pi. Okay, this cutoff frequency can be determined with what, with these nominations based on these two conditions in here, guys. Okay, and so we should create the examples of the what are solutions in here. Okay, the examples. Find the cutoff frequency of TF given by to what, Hz is equals to the 0.5 divided by minus 0.5 z over minus 1. Okay, this is our transfer function, but pulse transfer function. And so the solution can be summarized in these terms. Firstly, the z is replaced with what, z e j w, and then we can write that the h e over jw, which is equals to what, the 0.5 divided by minus 1, 0.5 times e j w. Okay, these are the terms in here, and so we have also a minus terms in here because this is the z over minus 1. Okay, and then we need to using the formula like E minus JW, which is equals to what, the cosinus W minus J sinus W, and then we can write that the H E over JW is equals to what, the 0.5 divided by minus 0.5 times cosinus W minus J sinus W. Okay, these are the case, right? And so after that we need to find out to what, the magnitude values in here, the magnitude of the H E over JW, which is equals to what, the 0.5 divided by 1 minus 0.5 cosinus W plus J 0.5 sinus W. Okay, we need to take to what, the absolute values of these terms, or in another terms we generate the real and the what imaginary part in here, and so it yields to the what, yields, I'm sorry, but this yields us to what, H E over JW, which is equals to what? The 0.5 divided by square root of the what? The 1 minus 0.5 cosinus W square plus 0.5 sinus W square. Okay, so in the following steps we need to determine to divide the finding WC at to what? HEJW, which is equals to 1 divided by square root 2. Okay, and this gives us to what? In these terms. First of all, we need to equalize these terms in here, just like this one. Okay, and then this relation can be written as the 0.5 square root 2, which is equals to the what? Square root 1 minus 0.5 cosinus W square, and also plus 0.5 times sinus W square. Okay, and so in the expansion form we have the 0.5 square root 2, which can be written as the 1 minus cosinus W plus 0.25 cosinus W square and 0.25 sinus W square. This yields us to what? 0.25, because the cosinus square plus sinus square is always to what? Always to 1. Okay, and so this simplify to the what? The 0.5 square root 2, which is equals to what? The 1 divided by 0.5 1.25 minus cosinus W can be given in here. Okay, and so if we take the square form of these things, this yields us 1 divided by 4, this yields us to 2, and so this terms is equals to what? 0.5 and 1.25 minus cosinus W in here, just like this one, and so cosinus W should equal to the what? 0.75, and so angular cutoff frequency is equals to what? The cosinus or arc cosinus 0.75. Okay, these are the R filter response or the cutoff frequencies of the R terms. Okay, after that we need to convert these terms in here at the 5 is the results of the R solution. WC times Fs divided by 2 pi must be equals to Fc, and so the Fc can be written as the cosinus over minus 1 0.75 times Fs divided by 2 pi. Okay, these are the cutoff frequencies for a given numbers or the transfer function in this case. Okay, so this is the what? The IIR filter response designs in the what? In the normal case at the discrete domain, guys. Okay, and so in the previous lesson we will talk about the designing the FIR filter, finite impulse response filters. Okay, because it has to what? It has a closed loop feedback in here.